Hi, we are continuing the discussion of sequential circuit, and in this lecture we will discuss flip-flops. And as we know that um, memory elements, oops, memory elements can be either latches, which we discussed in the previous part, or flip-flops. We know that latches are level sensitive; they are synchronized by the level of a clock, and we mentioned earlier that the flip-flop are um, edge sensitive. Um, so let's draw the clock here. This is the clock signal. Okay. For the flip-flop operation to be stable and correct, we have to pay attention to the following definition of times. The very first definition is that the input of the flip-flop has to be stable before the edge. Remember, this is the synchronization edge. So the inputs, they have to be stable before the edge arrives. We call this as the setup time. Also, the inputs of the flip-flop have to be stable after the edge for some time, and we call this hold time. Now, when the pause edge this edge arrives, the output of the flip-flop takes time, and let's say it arrives right here. So this is the delay for the output of the flip-flop, and we call this clock to cue delay. Okay. Now, uh, in some few cases, the edge of the flip-flop can I'm sorry, the synchronization of the flip-flop can be synchronized at the falling edge instead of the rising edge. So this is a rising edge, this is a falling edge. Sometimes the flip-flop operates here, but these are very few flip-flops. Most of the flip-flops operate on rising edge, which is when the clock goes from low to high. Okay. So we call this rising or positive edge, and this is falling or negative edge flip-flops. Okay. Now, in terms of really of block diagram, the positive edge flip-flops, typically when we draw them, okay, so the block diagram of the flip-flop, we typically refer to the clock as triangle, and we give the clock name. This triangle means that this is a flip-flop, right? If we have if we have on this triangle a bubble, it means that this is a falling edge flip-flop, which means it is synchronized by this edge. If we don't have this bubble, it means that we are synchronizing this flip-flop by the rising edge of the clock. Okay, so this is just some kind of definitions here. And now let's go with the business of explaining the flip-flops. Um, we will talk about three types of flip-flops. We'll talk about D flip-flop and JK flip-flop and T flip-flop. Okay. In practically everybody uses D flip-flop. JK and T flip-flops are just talked about in the academia. Nobody uses them in practice except very, very, very few cases. But to, for the completeness of the lecture, we're going to explain all of them. Okay, so let's start with D flip-flop. Okay, so D flip-flop. The D flip-flop, if we draw the symbol, it will be you have a input D. Whoops, sorry. input D and a clock, right? And we have this triangle that makes it a flip-flop. Without that triangle, it makes the latch. Then Q and then Q prime. The truth table for this thing is very simple. Basically, um, basically we have the D, the Q, right? Okay, and um, if the D is Q, it's the updated Q. If the D is 0, update Q will be 0. If the D is 1, update Q will be 1. And we refer to this as set operation, and we refer to this to as reset operation. Okay, so simply, really, what we can say is that QT plus 1 equals D. And notice that the D flip-flop is simple, and that's what makes it the most attractive type of flip-flops of all. Okay? All right. So the other type of flip-flops is called JK. Okay? So here is the JK flip-flop. The JK flip-flop um, um, is JK input J, K, and here is our clock. And by the way, if it is negative edge, we'll add the bubble. It's Q, it's Q prime. And here is how we describe the operation of this flip-flop. You have this J, K, okay? 0, 0, 0, 1, 1, 1, 1, 0, 1, 1. Okay, so this is 0, 0, no change. And 1, 1, we invert the T, and 0, 1 is reset the output to 0, and 1, 0 set the output to 1. So this is reset, this is set, and the inversion, we like to call it toggle. Okay, that's when we invert the output, and here, no change. Okay, so just just for the um, here we can say that qt, whoops, sorry, plus 1, which is this one here, equals jq prime or k prime q. Okay, so if you all right, so that's basically okay. Um, Finally, we have the T flip-flops, okay, and then the T flip-flop, okay, um, consists of, so T flip-flop consists of um, input T, output Q, Q prime, and a clock, okay, and the truth table for this thing is 0, 1. If it is a 0, then the output does not change. If it is 1, the output is the Q is inverted. So we say that this is no change, and this is toggle. Okay. Uh, so the output QT plus 1 is basically can be expressed as T Q prime or T prime Q. We can implement the T flip-flop in terms of a D flip-flop as follows. So here's my D flip-flop. This is my Q. This is my Q prime. My my clock. So this is the input T. So what do? I take the output. Whoops, sorry. And I XOR it with T and I push it to the D input. That's how I implement it. I can implement, so this is a T flip-flop using D flip-flop. I can implement T flip-flop using JK by shorting the J and the K. So here's J, K, okay, and it's the clock here. So I short the K and the J and connect it to the T input, and here is Q and Q prime. Okay, so as of completeness, and I know this is not in your notes, um, you can think of the D flip-flop. If I go back to the D flip-flop, the D, the D flip-flop can be implemented um, as um, two using two D latches. Okay, so here is a D latch, and here is a D latch. Okay, D latch. This is input. This is clock. This is input D. This is clock. Okay, and this is Q, Q prime, Q, Q prime. So how can I connect this to make it a flip-flops? So here is my D input, goes in here. Here's my main clock, goes to this, and the second clock is inverted to the next latch. This is Q, this is Q prime, okay? And the Q from the first latch is connected to the D of the second latch. Again, as a matter of completeness, this is how we implement JK, whoops, sorry, JK flip-flop. Okay, we start with an SR latch, SR latch, which is active low. This is Q, and this is Q prime, and then they are fed up with this. So this is the cross couple. This is the cross couple inputs, and then this input has, it's a three input NAND gate. Three input NAND gate. One input here is Q prime, and the other input is J, and the third input is the clock. Okay, and here is Q, and here is K. Okay, so this is how I implement JK flip-flop. I know these are not in your notes, but I'm just adding those as a matter of completeness for the topic. Okay, and um, um, finally, um, we have flip-flops with set and reset inputs, and those are set and reset. These are inputs that are added to the flip-flop. They are control inputs to flip-flops. Okay, so what does those do? The set forces flip-flop output, which is in this case Q, to 1. The reset forces flip-flop output, which is in this case Q, to 0. Now, somebody says, so why do I need these? Well, remember, these forcing happens, and watch, this is the important point, regardless regardless of clock, meaning they set the output asynchronously. Okay, so for instance, now if I have a flip-flop, let's say for example I have a flip-flop, D flip-flop, and here is my clock, the triangle. Okay, so this is D, and this is Q, and this is Q, Q prime. And here I have a reset. How does this operation is explained? So here's the truth table, reset. Okay, this is R, clock, D, and this is Q. Okay, so if reset is 0, which is in this case, it is let's say active low, the reset, then regardless of my clock, regardless of my data, the Q will be 0, and if there is a Q prime here, it will be set to 1. Okay, now if reset is in inactive, okay, so then when the clock rises, that upper triangle means when the clock rises and D is 0, then Q will be 0 and Q prime will be 1. And when reset is inactive and clock rises and the D is 1, the output will be 1 and Q prime will be 1. So these are the control input that can be reset or clear, um, and can be sometimes set. But most of the times they are active low reset. Okay, well, that concludes my lecture for um, the sequential elements. Thank you very much.